Hello. Welcome everyone to the ICTS VIGYAN ADDA. This is a new series that has been started by ICTS just in 2021. I think we just had our first, I think this is the third in the series. And it's a ICTS, for those of you who are here on this on the Zoom and the YouTube. Maybe many of you have been for many of our outreach activities. And this is a new one in which we thought we would try to target people who are keen on getting to know a little more about some of the cutting edge science that's happening around the world in various subjects. And we have actually had most of the talks by ICTS members conveying some of the exciting science that's happening at ICTS. So that's one of the purposes of the VIGYAN ADDA, and we will continue to showcase both our scientists as well as others in the Indian community who are involved in many ways with ICTS. So many of you know about ICTS. It's a center of the Tata Institute of Fundamental Research in Bangalore. It has its own researchers, like I mentioned, people like Subhro, Pranav, and others working in a number of areas in theoretical physics, mathematics, theoretical biology, and so on. And we have graduate programs in these subjects, and those of you who are in university, you should keep in mind many of the opportunities for students at ICTS. We have a summer visiting program, which unfortunately this year was cancelled because of the situation. We also have a long-term visiting program, whose deadline is now over, but every year around February, March, we advertise for people who can come and who would like to come and spend between a semester to a year. It's a very competitive program in getting very good applicants from around the country, and we encourage you to apply for that program if you're in your sort of master's, your fourth year or fifth year of your undergraduate education. And we have a number of other outreach events. The copy with Curiosity is now called Curiosity During Quarantine. This used to be held at the planetarium in Bangalore, and we hope to get back there eventually, but at the moment we are doing it online, and there is one coming up on insect society. So the copy with Curiosity covers a very wide span of topics and is aimed at the general public. VIGYAN ADDA, we hope, will have a lot of discussions from students and other young participants, and so please your questions, etc., in the chat box, and make this lively event. You'll have a fun time exploring the field of quantum matter with Subhro. Thank you.
Thanks, Rajesh, for that introduction. So I just want to, since the internet was cutting out a bit at the end, I just want to reiterate what Rajesh said. We want this to be very interactive, so please ask a lot of questions, both in the chat box during the talk, and at the end of the talk, you'll have, again, opportunity to ask questions. We have a very interesting talk lined up for you today. So it's titled Phases of Quantum Matter, by my colleague Subhro Bhattacharjee from ICTS. So a few words about Subhro. He's interested in quantum many-body physics and is, as I just mentioned, currently a professor at the International Center for Theoretical Sciences. He obtained his PhD in physics from the Indian Institute of Science in Bangalore, and he was a fellow of the University of Toronto and McMaster University in Canada from 2011 to 2013. And after that, he was at the Max Planck Institute for Physics of Complex Systems in Dresden, Germany, from 2014 to 2015. His research interests include magnetism, topological phases of condensed matter, physics of transition metal oxides, strongly correlated metals, and many-body chaos. He heads the Max Planck Partner Group on strongly correlated systems at ICTS and was awarded the Young Associate of the Indian Academy of Sciences from 2016 to 2019. With that introduction, it's over to you, Subhro.
Thank you, Pranav, for the kind introduction, and thank you, Rajesh, for introducing the series. I've been enjoying this talk. The series, the previous talks by other colleagues of mine. And so what I'll do is in the next hour or so, I'll tell you about some of the things that I'm excited about and our group is doing in broad sketches. And in particular, the aim of this talk would be to explain to you this picture that you see in the background. This is, of course, an artist's impression of what quantum spin liquid is. And I'll take you through various stages, through pictures and discussing the associated physics to explain to you what this really means. Okay? And so I'll sort of divide my talk into three parts as I'll elaborate on this as I go along, but with hopefully a lot of scope for discussions. Okay, good. So let me start. Actually, there are various points, starting points to try and understand the nature around us. Okay, so we can take these paths and it would lead us to explore various areas of natural sciences. And the particular story that I want to share with you today will revolve around materials, something that I am very much interested in. And I think as you saw in the abstract, this basically controls our lives more and more these days. Okay, good. So the talk is going to be divided into three parts. I'll start by sharing some of the basic principles of how we think about matter around us and share with you particularly important and central organizing principle that we have come to know about to try and understand states of matter. Okay, and then I'll take a brief interlude to explain to you something which might sound intimidating, but I'll try to do it through pictures and hopefully we will be on the same page. This is about quantum entanglement. Okay, and finally, I'll bring these two things together to explain to you what is known as quantum states of matter. Okay, so these are the three things that are on the agenda today, and hopefully we will hopefully we'll have an exciting hour coming up. Okay, good. So the starting point, as you know, to try and understand materials is a periodic table, which is this table, the first, this idea of systematically putting elements together was by Mendeleev. And these elements are, in the course of the history of the universe, these were made inside the stars and other celestial bodies, and we find them on Earth. Some of them stable, some of them unstable, radioactive, but they can be arranged in this form in terms of their atomic numbers, etc., in form of this periodic table. So once they're around on Earth, what has happened in course of the history of the Earth is basically that as the Earth has evolved, these elements have been put together in sort of a cauldron, and we get various kinds of compounds. We can mimic the same kind of processes in labs, and we get various kinds of compounds. Okay, so this is basically what we want to try and understand. So to say, the interesting or the magic materials. By magic, I of course mean things which are have particularly functional properties which are useful to us, and we will try to understand them. Okay, so so the particular question that we would like to ask is, what are the basic organization principles behind these functional properties? Okay, and we will try to understand two such basic organizing principles, which makes these things, which explains the various functional properties to us. Okay, so in particular, we will try to understand various things like crystals or magnets or metals, things called superconductors, and finally quantum spin liquids. This is the picture that was there in the title slide. And what I'd like to point out from the outset is that as we go from left to right, somehow the quantum mechanics becomes more and more important. Okay, and even though everything is quantum, somehow the quantum effects become more and more prominent in understanding these, so to say, material surfaces of matter, and that's what we want to try and understand. Okay, so let us start. Okay, so our strategy for this talk, since this is a diverse audience, the strategy would be to discuss examples and associated physics through pictures. Okay, and of course, after the talk, we can decide to try and understand the relevant mathematics, and of course, we would need to do courses in physics, etc., to understand. And I hope that a lot of you who are pursuing physics would be interested in doing that. Okay, and once we discuss these examples, we will try to illustrate the underlying organizing principles which go beyond the examples themselves. And finally, we will summarize. Okay, good. So let's go back to the periodic table and take an example. And this is this thing that we are familiar with, carbon, which is situated here in the periodic table. And let's take carbon atoms. Okay, so the basic unit that we want to try and think about is the carbon atom. And here is an actual picture of a carbon atom under a field emission electron microscope. And this basically tells us the electron cloud that surrounds the carbon nucleus. Okay. So of course, we are not interested in one carbon atom, but we want to put many of them. Okay, typically in things around us, we see 10 to the power 23 number of carbon atoms, and we want to say take that many carbon atoms and put them together in a box and try to understand their properties. Okay, so let's try to do that. We must remember that all carbon atoms inside this box have identical properties. And when we put them together, they interact with electromagnetic forces, and the nature of which are complicated themselves, but they share some common features with things that we know, like the Coulomb's law. Okay, so just to remind, Coulomb's law is basically 2-point charges interact with each other through this force, which is attractive for positive and negative charge, and is repulsive for two positive charges or two negative charges. Okay, so a particular property of these interactions, which is similar to that of Coulomb's law, is that they only depend upon the distance between two carbon atoms. It does not depend exactly where the two carbon atoms are. but they only depend upon the mutual separation of the two carbon atoms. And that's going to be the central feature, which is going to be important for our discussion. Okay, good. So this is what we want to start with, that there are two carbon atoms, and irrespective of where they might be here, they might be here, or they might be here. As long as the separation is same, their forces are the same. Okay, good. So because this force does not depend upon the individual position of the carbon atoms, we say in more concrete words that this interaction has translation symmetry. In other words, it does not depend upon where the two carbon atoms are. It just depends upon their mutual distance from each other. Okay, and this is one important property, and not the detailed form is not important. Okay, good. So now, if I am dealing with interactions which are translation symmetric, or in other words, it does not depend upon the location, we expect the properties of the system to be also translation invariant. Okay, and that's the expectation. But this, of course, is not the complete story. There is a problem with this expectation, and this was first systematically pointed out by Landau in the sort of 50s and 60s of last century. Okay, the point is as follows. At high temperature and low pressure, this expectation that the properties of the system are translation invariant is turns out to be true. And what we have, and this is certainly true in a fluid or a liquid or a gas of carbon atoms, where the atoms are sort of moving around in the box, such that if I look at a small region inside the box, say this region, and think about the average density inside that box, okay, over time, we will find that over time, the density inside that subpart is uniform. Okay, so if we average the density over time, we will find that it is uniform, and hence the property of the system does not depend upon where I draw the box and its translation invariant. But the problem comes when we think about low temperature and high pressure. Okay, and where we have crystalline solids, and this we know for carbon. We know two very familiar crystalline forms. One is a graphite. That's those are the things that make the lid of the pencil, or say the diamond. Okay, and these forms are certainly not. The density is not uniform even after time averaging. If I have a piece of a diamond, the carbon atoms are arranged in this particular form, and they just don't move around with respect to each other over time, unlike the gas or the liquid. Okay, so it is in that sense the average density, even after time averaging, it is not uniform, and this is what is known as breaking of translation symmetry. Even though the underlying laws are translation invariant, the base structure of graphite or diamond does not seem to exhibit that property, unlike the gas of carbon atoms. Okay, so this is very surprising when put in this way, and that even though the underlying interactions are translation symmetric, the properties are not. Okay, and this statement is summarized as the state breaks spontaneously translation symmetry. Okay, and this breaking of translation symmetry turns out to be one of the greatest organizing principles that we have discovered in physics. and starting from lambda. Okay, and this spontaneous breaking of symmetry, here the translation symmetry, leads to distinct functional properties. The particular way that translation symmetry is broken leads to functional properties. And for example, say in graphite, where we end up with having these flaky layers. So each layer is sort of very weakly coupled with the other layer, and we have this two-dimensional structure on top of each other, gives its characteristic property to graphite, which is why we use it as a lid of a pencil, so that each of these flakes sort of stick to the paper as we rub the pencil against the paper. And this property, this gives this layered flaky structure, this particular way of translation symmetry. On the other hand, in diamond, where we have this particular form of arrangement, we know that its properties are very different from that of graphite, and it is hard, it is certainly not flaky, most of them are transparent and reflects light. So the particular way that the translation symmetry has been broken is reflected in the properties of the materials themselves. Okay, it is true even though the carbon atoms are same. Okay, so this is one major aspect. So let's try to understand this in more detail. And to make the point again, it is the same carbon atoms which gives the graphite or diamond, in the sense that if I take one carbon atom from graphite and one from diamond, you cannot really distinguish them, and you can sort of switch them from one to the other. Okay, and so the property of these particular properties of graphite or diamond is not a feature of individual carbon atoms, but a property of the whole assembly. Okay, and this is what the spontaneous symmetry breaking leads to. It leads to collective effects, which is an emergent phenomenon in the sense that it cannot be attributed to any one of the participating atoms. And this was basically forcefully enunciated by Phil Anderson in 1970s. He pointed out that many is different, in the sense that in many in systems with many basic units, you have these collective effects, which are sort of collective behavior of the entire assembly, which gives to new qualitative behavior, which cannot be attributed to any one of the individual members. Okay, so that's one point. The next point is that this, once you find out this spontaneous idea of spontaneous symmetry breaking, it just applies beyond graphite and diamond, and in the sense that all crystalline materials break translation spontaneously. For example, common salt, crystals of common salt is made out of sodium and chlorine arranged in this particular way. And so are other crystals that you see around you. Okay, and this kind of idea can be extended to other things like superconductors, magnets. In particular, we will discuss magnets. And so this forms really one of the organizing principles that can be used to study a whole lot of things under the same umbrella. So to make this point that many is different more concrete, we should say that many is really different in the sense that they give rise to collective phenomena, but many is not arbitrarily different. There is some rhyme and reason, and there are some governing organizing principles, so which can be used to try and understand all these different forms. Okay, so finally, the third thing is how do we understand these spontaneous symmetry? So what really happens is that at low temperatures, in case of crystals, these atoms get stuck into this crystalline motif. For example, for this sodium and chlorine common salt, they get stuck into this motif. And we have to really wait for a very long time to see this motif being destroyed, and the system recovers the symmetry. So the question is that how long should we wait? Okay, and it turns out that at low enough pressure and temperature, we should wait for about 1 over the number. Sorry, this is wrong. This should be n. Okay, the number of atoms, and this is 10 to the power 23 seconds. And compared to the kind of timescales that we know, this timescale is really very long, and for humankind, this is really forever. And so this is basically the reason how spontaneous symmetry breaking emerges. And of course, there is a lot of mathematics and rich physics behind this, for which we, to understand this, we have to go to physics grad school to understand how this incredibly large time scale emerge in these kind of systems, in this assembly of materials. Okay, so this is basically one of the governing principles of this rich world of emergent phenomenon, and that we see all around us. And this not only encompasses symmetry breaking that we have just discovered, but other things in which structures emerge out of many basic units. And here are some arbitrary examples that are taken from around us. And so we can go and ask, how do this emergent phenomenon occur in these different kinds of materials, whether it be a collection of stars and planets, whether it be the vortices in weather patterns, or fluid turbulence, or life itself. Okay, so these kind of structures, how do they emerge out of basic units? Okay, and so this symmetry breaking is one such organizing principle through which structures can emerge, and it is one of the central principles that physicists have discovered over the last century or so, that gives rise to, that explains how structures can emerge in materials. Okay, so this is one of the things that I wanted to emphasize as the first part of the talk. At this point, we can sort of take one or two quick urgent questions. If there is a burning question regarding what I just said, we can have them now, or we can just wait till the end of the talk to try and address all the questions. I can see a lot of questions coming through, but if there is one or two urgent questions that Anupam wants to point out, then I can try to understand, address, or maybe go on till the end of the talk and address all of them.
Sure.
So, Anupam?
So yeah, Professor Subhro. So you have already explained it in detail, but there are still a few questions on both YouTube and Zoom, asking you to reiterate the translation symmetry breaking in short copy.
Okay, so you see that, let me just write here. So you see that when we think about Newton's law, as I explained, that it only depends upon where the first atom is and where the second atom is. Okay, it only depends upon the distance of separation of the two atoms. Those two atoms can be here at ICTS, or it can be somewhere else. Okay, it just needs to be the difference. So as long as I keep the distance same, the force between the two atoms are going to be same. So such a force, if I take these two atoms and translate from one place to another, the force remains same between the two atoms. This property is called translation symmetry. Okay. Now, since the force itself is translation symmetric, we expect that any feature of these system is going to be, all the properties of the system are going to also obey this feature of interaction between the particles. Okay, so that's the reason why we expect that naively that all the properties of the system are going to be translation symmetric. And this is true for, say, the gas, where I have these atoms randomly moving around in this box, so that if I look at a time averaged position of the atoms, they are everywhere. Okay, so this average picture does not favor one location in the box compared to the other location. So in that sense, the property is translation invariant. But in a crystal, let's say a single layer of graphite, the atoms are sort of stuck to their positions. So over time, this atom does not move arbitrarily compared to these atoms. Okay, so even though if I average over time, of a very long time, I would keep on seeing that if I measure the density of the atom here, I would never find an atom. But if I measure the density of the atom here or here, at particular places with particular distance of separation, I'll always find an atom. So the fact that unlike the fluid, the time average picture is not uniform throughout the space. That's the essence of time translation symmetry breaking. Okay.
Thank you, Professor Subhro. I think we can proceed with the talk and take remaining questions towards the end.
Okay, good. So let's turn to the second point and towards quantum mechanics, and try to understand what we call electronic phases. Okay, so that's where we want to go. And so we sort of understood crystals. We want to go towards these other things. And as we pointed out that the quantum effects increase. So what we are interested in is trying to understand the properties of these electrons. And what exactly these electrons are doing in these materials to give them their particular functional properties. Okay, and for this, we would need to understand some basic features of quantum mechanics, which I'll now turn towards. Okay, and I'll explain them in only basic rules that are obeyed by quantum mechanics, and that's how we would try to go along and see how those rules are applied. Okay, so let's do this in steps, basically 3 steps, but let's first recap how classical mechanics work. Okay, so the classical mechanics for motion of a particle along a path like this, we need to specify at any point of time the position of the particle and its velocity. Okay, so if I have 2 particles, I need to mention the position and velocity of the first particle and the position and velocity of the second particle at the same time. And if I have more particles, that's how I go along. I mentioned the third, fourth, fifth. So this is in principle how classical mechanics work. But this is very different from quantum mechanics. And this is sometimes it appears counterintuitive because we always have classical mechanics in the back of the mind, but which is why quantum mechanics appears mysterious to us. But it is a well formulated framework to understand properties of very small particles. Okay, so at the heart of quantum mechanics is what is called superposition principle. And this is what we need to learn now. And I'll explain this using something that many of you must be familiar with, is the double slit experiment, which is a very famous experiment when gives us a lot of ideas of how to try and understand quantum mechanics. And let's try to understand that. So the experimental setup is made out of 3 parts. It is made out of an electron gun, which spits out electron like the old CRT TVs that we had about 15 to 20 years ago. So then there are two identical slits. So this is like a board which two small sections cut out and which are sort of close by, and then which allows electron to go through only through these slits. And then I have a screen which can detect electron. Okay, so then the electron gun spits out these electrons, and they go through the slits. Okay, so classically we would expect that the slits are close together. There is one central region of high intensities, and that's it. But when we perform the analogs of this experiment, we find that instead what we see is this whole set of high intensity regions, as we would have expected from something like a water wave, etc. So in some sense, the electron is behaving like a wave. Okay, and that is, as I'll show, is at the heart of quantum mechanics and what is called the superposition principle. Okay. So before we go there, let's try to recap. So if we close one slit, say we close slit 1, and then we see that the intensity pattern disappears. Similarly, if we close slit 2, we see that the intensity pattern disappears again, and we have one bright intensity. Okay. Similarly, if we try to watch which path the electron is taking, say by shining a light, try to see the electron as they're going through, say, slit 1. Okay, so I shine a torch, try to see which path the electron is taking. What happens is that if I try to do that without closing the slit 2, even then the intensity pattern disappears. But what is even more weird is that I always, unlike the wave which goes through the two slits at the same time, I always detect a whole of an electron. I never detect a part of an electron going through one slit and the other part going through the other slit. So the electron always is detected as a whole, but when it is detected, it affects the intensity pattern and it disappears. Okay, so then the point is, how do we reconcile this? And this is what quantum mechanics does for us. And so it says that it assigns possibility of electron going through slit 1 or slit 2, and this is denoted by these funny symbols which quantum mechanics uses. So this symbol 1 denotes the possibility of the electron going through the first slit, and this symbol 2 denotes that the electron going through the second slit. So the superposition principle of quantum mechanics says that the general state of the electron is the sum of the two possibilities. And that's denoted like this. Okay, so the first possibility is going through the first slit, and the second possibility is going through the second slit. And in general, we need to add these possibilities at the same time. Okay, so that's the superposition principle. We will not go into further. We can discuss this after the talk, but this is the first rule of quantum mechanics. The second rule of quantum mechanics is that once we try to detect which possibility is it taking, then the superposition principle just chooses one of the possibilities consistent with the observation. Okay, so for example, if we detect it going through this path 1, this sum of possibilities reduces to this single possibility. Okay, so that's rule number 2. Okay, good. So this we need to try and formulate it in terms of electrons, which we want to try and understand. Remember, we want to understand electronic phases, and we want to try and understand the superposition principle of the electrons. Okay. So in principle, what we want to understand is the superposition principle for the electron spins. Okay. So it turns out that the electrons have an internal degree of freedom called a spin. It's roughly like electron moving clockwise or anti-clockwise, and that's the only two possible ways that's allowed. But one should not really think very seriously about that picture, but one should really think more in terms of this two slit possibilities, that it can either be this possibility or this possibility. Okay, and we will call that if it is this possibility, we will call that the electron spin to be up, or if it is this possibility, we will call that electron spin to be down. Okay, and that's it. So the superposition principle, now we take from this double slit experiment, tells us that the general state of the spin of the electron is a superposition of these two possibilities. Okay, so that's the superposition principle for the electron. Good. So now let's try to go towards the essential features of the third essential feature of quantum mechanics, which is superposition principle applied to many electron systems. Okay, in particular, let's take superposition principle for two electrons. Okay, so now there are four possibilities. Each electron can be, so I have electron 1, I have electron 2. Okay, so each electron have two possibilities, so there are four possibilities. So the first electron can be up, the second electron can be up. So that's this one possibility, which we denote by this funny state up, up, where this first entry is for the first electron and the second entry is for the second electron. Okay, good. So that's the notation. It just says that this is one possibility. The second possibility is this. The first electron is up, the second electron is down. Okay, and that's this. And similarly, the other two. Okay, good. So that's the four, those are the four possibilities for the two electron spin state. Now let's apply the superposition rule. The general state is a sum of all the four possibilities. Okay, so that's the superposition. Good. So that's all we need to know about the two electron state, and this would be very important for the rest of the talk. In fact, what we will do is that we will take a slightly different state. Instead of having this four possibility, we will only take these two possibilities to make our life simple and to connect with experiments. So we will take this particular possibility, which is this. And so this kind of superposition can be engineered in either in labs or more generally, naturally in certain materials. Okay, good. So this is called what is called EPR state, after these three famous people who made this notable: Einstein, Podolsky, and Rosen. Okay, so even though Einstein in particular, they never really thought that quantum mechanics is the complete theory, he made remarkable contributions, and one of them is this EPR, this idea of an EPR state. Okay, so let's take this state, and let's, since we have been drawing cartoons instead of writing the symbols, we will denote it by this cartoon that there are two electrons. The first electron is here, and the second electron is here, and then they are in this superposed state. Okay, good. So let's try to find out the weird features of these EPR state. Okay, so let's prepare 2 electrons in this EPR state, and let me keep one with me, and let me share the other electron with you, both in this EPR state. So that's here. So you are sitting at your home or wherever you are, and I am at ICTS. We have this EPR, 2 electrons belonging to this EPR state in the superposition. Now, suppose I measure the spin of the electron that I have. Okay. Now, the point is that this is the state, and if I find the state to be up for my electron, then the EPR state, as we pointed out, must reduce to the state which is in accordance with that measurement, and that's this first half. So, and in this first half, the second spin is down. So if you measure, you must find your spin to be down. On the other hand, if I do the find it down, you must find it to be up. Okay, this is the weird feature. Okay, and you notice that this means that arbitrarily far apart, it seems that my measurement seems to affect your observation. Okay, and this non-locality is what bothered Einstein and his collaborators, and this, as we understand now, is a hallmark of quantum mechanics. We may feel very uneasy about it, but that's the feature of quantum mechanics. That's the feature of the nature around us. Okay, and so this particular feature is called quantum entanglement, and this has no classical counterpart. Okay, so this non-local feature about this superposition that I might measure up or might measure down, but once I measure up, you must measure down, and vice versa. This is what quantum entanglement is, and there is no classical counterpart, and it has been repeatedly tested in experiments, and we find no exceptions to this. Okay, good. So these are the 3 essential features of quantum mechanics that we will need to try and understand things. Okay, good. So the first one is the superposition principle, that we should add all the possibilities that are around. The second is the superposition principle applied to electron spins. And the third is this non-locality of 2 electron spin states through the EPR type of state, which gives us the idea of entanglement. And this third thing, all these things, but this in particular, this third thing is a remarkably unique feature of quantum mechanics. Okay, so this is the thing that we will try to okay, so that is a breezy recap or introduction to quantum mechanics. Okay, I see that I am slightly behind schedule, so I'll not take questions now. I wanted to take questions at the end of this, but I'll just start the third part, and maybe we will have all the questions at the end. Okay, good. So what I'll try to do is to now take these 2 things together and apply them to understand what quantum states of matter are, and something that has caused a lot of excitement in the last 30 years or so, in particular the last 10 years. Okay, good. So let's go back to electronic phases. So we are now ready to learn about them. And what we want to understand in particular is what are the electrons doing on a lattice. We understand how to form a lattice. And in particular, what I have drawn here is a square lattice. And I would like to try, for simplicity, I could have drawn this honeycomb lattice for graphite, or this diamond lattice, but then I would have to draw complicated pictures. But let's try to do this on square lattice. But there are examples in nature where we realize this kind of square lattice, very notable examples. Okay, but for us, it would be just simplifying in terms of pictures. Okay, good. So I have square lattice and I have electrons on the lattice. Let's start with one electron. So this electron can move around in this lattice. It can jump from one lattice side to another. So notice that I could have used the principle of superposition to explain this, because this electron can stay at any lattice site. All these are possible possibilities for the electrons to stay. So the general state is going to be the superposition of all these things. Good. Okay. So so let's so that's what a single electron does. Now let's think about many electrons. In particular, I have drawn two here, so they move around on the lattice. And when they are freely moving around like this, what we get is a metal. So all the nice metals that we have, gold, etc., basically can be explained by this picture of electrons which obey quantum mechanical laws moving on the sides of the lattice from one side to another, and another, like what we explained in this picture. Okay, so that's how we can try to understand metals, and we can try to explain all the metallic properties. So like why gold shines and why silver shines in a different way and things like that, using this basic quantum mechanical laws. Okay, even weird, we can explain very exotic phases of matter like superconductor, when instead of a single electron, electrons always move together in pairs. Okay, so that's called the Cooper pair, and they can move together. They don't move on their own, but they move together always in pairs, and that's when we get what is called a superconductor. But we won't try to go into the superconductor, because we want to see the example of an entanglement in a slightly simpler situation. So what we will try to do is not take this route, which we could have taken, but do something else. We will try to understand what is a slightly complicated situation, but more rich, and in the end, somewhat simple. Okay, so we will try to talk about this situation where there are lots of electrons, and the electrons interact with each other extremely strongly, and we will get magnetism. Okay, so let's remind ourselves about the Coulomb's law again, that two electrons repel each other using Coulomb's law. So if I put two electrons and only think about Coulomb's law, they want to stay as far apart from each other as possible. Okay, good. So that's all we need. Okay, so we must remember that the electrons would like to stay as far apart from each other as possible to be consistent with Coulomb's law and be in a low energy state. Okay, so we had two electrons, but now what if we have a lot of electrons? In particular, we have one electron for each side. Okay, so at every site I have one electron, and they are trying to stay apart from each other as far as possible. Okay, so the minimum energy is to put one electron at every site, and that's the farthest that they can be from each other. Okay, so now if an electron tries from this configuration tries to move, say for example, if this electron tries to move to this point, then it bumps into another electron, and now we have two electrons very close together, and that costs a lot of energy, because I am putting two like charges together. That costs a lot of Coulomb energy, and this is the reason why the electrons, unlike the previous picture, do not move anymore, and they sort of localize. Instead of a metal which is formed when the electrons can freely move, what we have is now an electrical insulator. Okay, and this is really what is called a Mott insulator, after Sir Neville Mott, who thought about this kind of physics in the middle of last century. Okay, So it is because of this Coulomb interaction that the electron sort of stop moving and sort of localizes at each lattice site. Okay. But now we have learned something a few minutes before, that the electrons also have this internal degree of freedom, the spin. Okay, I have so far said nothing about the spin. Okay, so we have said that the electrons sort of positionally localize, but what happens to the spin? Okay, what are these spins doing? We know that they can be up or down, but what are they doing? Okay, in this system. So at this level of description, the electrons, the spins can do anything. Some of them can be up, some of them can be down, and they does their own thing for every electron. Okay, so they can be up or they can be down, or the all kinds of spin orientations for each of these electrons are allowed. And this is exactly what happens at high temperature. So the spins are doing their own thing. Some of them are down, some of them are up, and they can change from up to down on their own without bothering the other electrons. And this is what gives us a high temperature paramagnet. Okay. But what happens is at low temperature is that when we cool down the system, even though the electrons can be all up, can be up or down, it's suddenly, just like this graphite which breaks translation symmetry, it suddenly can choose, all of them can choose to be all pointing up, like or all pointing down. Okay, and so both these possibilities are allowed, but once this one possibility is chosen, then the other possibility is just not allowed. And just like the crystal, which breaks translation symmetry, now what I have done is that this up-down symmetry of the spin, which are two possibilities, that has been, I have chosen one of them. And in other words, now I have broken these up-down possibility or spontaneously. Okay, so this is what gives us a ferromagnet. Okay, and so when I have this, this is how a bar magnet behaves, or the fridge magnets that we have at home behaves, that all the spins are pointing in some direction, breaking spontaneously the spin root, the up-down symmetry. Okay, and so you see that something that we had discovered in context of crystal, the spontaneous symmetry breaking, now I have applied to a completely different circumstances, which is the magnet, and have got a description of a ferromagnet. Okay, good. So that's what it is. But that's something that we have learned, and it is important in the sense we have the magnetic memory or the compass needle, etc., which are extremely important and have played an extremely important role in the in our technology. But this is something that's old in the sense that we have learned this. Okay, and what we in the next 5 to 10 minutes, what I want to talk about is basically a new way, a new organizing principle beyond this spontaneous broken symmetry, which takes advantage of this entanglement that we learned from quantum mechanics. Good. So this new possibility, to understand this, we need to go back to what we learned about the EPR pair. So I remember I have 2 electrons. One electron is up and the other electron is down, and the other possibility is that the first electron is down and the second electron is up. And the quantum superposition principle tells us that I can take sum of these 2 possibilities, and that's what the EPR pair of electron was. Good, and that's the picture. Good. So now let's think about electrons on the lattice. Okay, so so these are the electrons, the red dots. I've moved them on the lattice sites for the convenience of drawing pictures. So let's consider this electron. Okay, now let's consider this electron to form a EPR pair with its nearest neighbor, and that's denoted by this the same kind of symbol that I have been using. Okay, so this means that these two electrons form a state like this. Okay, so now let's think about what the other electrons are doing. Okay, so they also form EPR pairs. Okay, I'm not telling you why they form EPR pairs. That would take us to learn a lot of physics and chemistry, but let's assume that the other electrons also form EPR pairs. Okay, but this is just one way the other electrons can, or the different electrons, one at every side, can form EPR pairs. Okay, so this is just one of the possibilities when I have many electrons. The other possibility is that it just forms EPR pairs, but with its right partner. Okay, so that's this. Or it can form EPR pairs with the partner at the top, or in some random way like this. So these are all the possibilities. That the rule is that each electron forms an EPR pair with one of its neighboring electrons, or maybe the one at far away, but it always forms an EPR pair. So all these are possibilities as far as the formation of EPR pairs are concerned. Okay, so this is just plain and simple applying EPR pair, the idea of formation of EPR pairs to many electron systems. Okay, good. So now let's apply quantum superposition principle, which says that if I have many possibilities, I should take the sum of all possibilities. Okay, good. So if this is one way of forming EPR pair, this is another way of forming EPR pair, this is another way of forming EPR pair, and fourth and fifth. So here I have drawn where an EPR pair is formed out of two electrons which are not close by, but those are also possibilities. And then there are countless such possibilities. So the superposition principle tells us that the general state is like the sum of all these possibilities. Okay, so this is something that we need to try and understand. And when we try to understand this, we see that just like the EPR pair, now I have the EPR pair had this non-local feature of called entanglement built into this. What I now have is many EPR pairs and a superposition of such set of EPR pairs, which gives rise to extends the same idea of quantum entanglement, but now to many electrons. Okay, so it is basically the EPR idea extended to many electrons, and the idea of quantum entanglement extended to many electrons. Good. Okay, so this is exactly at the heart of what I call the quantum state of matter, because as we pointed out that quantum entanglement does not have any classical classical counterpart. So if I have such superposition of EPR pairs, then I would have a highly quantum entangled state, which would be extremely non-classical, in the sense that the quantum mechanics would be manifestly important in such a state of matter. Okay, good. So let's try to go this. In general, this quantum state of matter are classified by such forms of entanglement. I have discussed one particular kind of entanglement, but general the idea is that they give rise to these kind of entanglement patterns formed out of these EPR type of ideas. Okay, good. So I have this kind of state. Okay. So let's try to close this talk by asking two questions. Okay, so it seems that I have just pulled it out of a hat, but do these things exist? Okay, and what are the fallouts? entanglements. Okay, so we asked the same kind of questions for symmetry breaking, but now we try to ask the same question for this idea of entanglement pattern. Okay, good. So let's take them in turn, and let's first ask, why do they exist? The answer is a ubiquitous yes, and we know that of many kinds of this entanglement pattern that exists, and some of the early things that we know very well are goes by the name of quantum Hall effect or topological insulators more recently, and these are complicated things. I'm not going to explain to you these in any detail, but let me just point out one form of entanglement pattern which have possibly been discovered recently, which is seems to be the most weird kind of quantum entanglement that we have encountered. And that seems to happen in this very plain and simple looking black crystals of ruthenium trichloride. So I mean, the name does not mean much, but this is this compound made out of ruthenium and chlorine arranged in a particular form, which we can discuss after the talk. But what has recent experiments and theoretical understanding led to us is that the low energy properties of these of the electrons inside this material presents an intricate, slightly different, but intricate version of this entanglement pattern that we have learned in terms of EPR pairs. This picture that governs the low energy properties of this system. Not exactly this EPR picture, but very close to this. Okay. Of course, this needs to be settled, and that's what is being that's happening in a large number of labs and groups, including ours at ICTS. But that is essentially the picture for this talk, that I have this electron spins. Now I can explain to you. Sorry. Yeah. So, so there are these spins, and then there are these wriggly lines. These wriggly lines are basically an artist's impression of what entanglement is. Notice that since it's a highly quantum state, unlike a magnet, I cannot really draw classical pictures for this. And this kind of state is what is called a quantum spin liquid, because it basically does not give rise to a frozen pattern like a ferromagnet or a crystal. So the spins are fluctuating. It can be up or down, but at the same time fluctuating in this quantum entangled way. Okay, so this is at the heart of quantum phases of matter, and the things that are of extreme interest to a huge number of people. Okay, so almost at the last slide. So what are the fallouts? Okay, so this entanglement pattern provides us a completely new organizing principle, or a new kind of emergent phenomenon, which and it opens really a lot of questions going back to some of the fundamentals of physics and the way we learn the various kinds of condensed matter and other areas of physics, try to understand what are the implications of this organizing principle, just like the organizing principle of symmetry breaking led us to a plethora of questions that we now understand quite well. Okay, so what are the functional properties? We notice that the spontaneous symmetry breaking gave rise to a bunch of functional properties like ferromagnet or the or this graphite or the diamond properties. But what are the functional properties of this emergent phenomenon? So again, this is something that would take a whole talk to explain, but what it turns out is just in a single sentence that this entanglement pattern allows us for efficient algorithms for calculations. Okay, and this goes under the name of quantum computation. And using this entanglement pattern, it turns out that we can implement some of these algorithms if we make our computational devices, or so to say, quantum computers, with these materials which support these the various kinds of entanglement patterns. Okay, but we are really scratching the surface of these kind of physics, and a whole lot of things needs to be unearthed, and that's what the entire community is looking for the next several years. Okay, good. So that's where I'll stop. Sorry, I've got over time, but this is the group at ICTS. These are the postdoctoral fellows, Abhas, Abhishod, Adit, and the PhD students, Animesh, Arnab, Monica, and Vasudev, who really do all the hard work in the group, and some of the very interesting things that are going along the lines that we just described. And these are other collaborators and funding agencies. There are too many to for me to try and name, but the lot of things have happened from these collaborations, and the funding, of course, has helped us to do all this research. Okay, so with that, I'll summarize. So the first point is that the various kinds of emergent phenomena are all around us. Okay, and these forms the basis of all functional properties that we see. One of the, and I have discussed two of them. The first organizing principle that that forms the basis of this emergent phenomenon is spontaneous symmetry breaking. Okay, and this gives rise to conventional phases like crystals, bar magnets, etc., etc. The second organizing principle, which is more quantum, are patterns of quantum many-body entanglement, and I have discussed this idea of EPR-based quantum entanglement pattern, and this gives rise to what are called quantum states of matter, like quantum Hall effects, spin liquids, etc., which might be useful for other things. So these two principles are extremely deep and fundamental organizing principles of nature, which occur at the many-body level, and there are no single particle analog of these entanglement patterns or the spontaneous symmetry breaking that we can have. Okay, and we need to try and understand what does it mean for the nature and universe that we live in. And so this is the search that we need to embark on, and the interplay of these two organizing principles is something that we have just started to understand, and all of you who want to take up physics as your career, you are welcome to join. So with that, I'll thank you for your attention, and I cannot summarize it better than this cartoon of Calvin and Forbes by Bill Watterson. So it looks like that we have an exciting journey ahead. Okay, so thank you.
Thank you, Professor Subhro, for the wonderful talk. We'll now move on to the question and answer session. Meanwhile, you can have some water if you have.
Sure. I won't mind. I mean, but you can just start with the questions. And
yes. So the first question is by Deepam, and he wants to know: can electrons be entangled in more than one observable? If so, could position and momentum be two such variables, and thus knowing position of one and momentum of another could be completely determined? Yeah, that's the. And the remaining part of the question is.
Can you repeat the question? I don't think that I understood the question very well.
So the question is: can electrons be entangled in more than one observable? If so, could position and momentum be two such variables? And thus, knowing position of one and momentum of another, could we completely determine the system in phase space without any uncertainty, or something similar but with perpendicular spin components as the entangled observable?
Yeah, so I think that there are many parts of this question. I'll try to arrange them and answer them in the way that I understand. So first of all, different components of the electron degree of freedom can be entangled? The answer is yes. So the simplest example of this occurs in a huge number of compounds which are called spin orbit coupled systems. So in in those class of systems, sorry, I'm being a bit technical, but this is going to be precise. In those systems, the spin and the orbital degrees of freedom. So, by orbital, I mean the hydrogen atom, 1s, 2s, 2p. So let me just write it here. So the hydrogen atom, 1s, 2s, 2p. So 2p has px, py, pz, and then there are d orbitals. So you can think about the electron and I don't know what is happening. Let's see. Yeah, so the orbital, say I'll draw the p orbital, and the spin of one electron together getting entangled with, say, the spin, the orbital of another electron together, and this would give us a spin orbit entangled EPR pair. Okay, and we can try to extend these ideas to other kinds of orbitals or components of the electron wave function and try to entangle them. Okay, so this is one part. So the next part is that whether things like position and momentum can be entangled. You see that it does not. So the entanglement is between the two different degrees of freedom. Okay, so you can certainly think about one electron in a position basis and one electron in a momentum basis, and then try to think about a wave function in entangling them. On the top of my head, I don't know how to write down that wave entangled wave function, but you can think about them. But you cannot beat the uncertainty principle, because this has to do with two different electrons. If that's I understand the question in some sense. Okay. Yeah.
Okay. Thank you for the answer. I'll move on to the next question.
Yeah. If there is, if I haven't answered any part of your question, feel free to ask your question again.
Okay. So yeah, I'll move to the next question. Is there any? So Prashant is asking, is there anything like stimulated symmetry breaking?
Stimulated in the sense of trying to do something from outside?
I think so.
Okay, yeah, of course, there are such things. Okay, so there are definite ways, but then that is not spontaneous. You are trying to push things to do. So for example, you can think about say an artificial situation where you sort of, and it's not really artificial. This is done in what are called cold atom systems. What you can do is that you can think about a bunch of atoms like the rubidium atom, etc. And this is regularly done in labs, say, for example, in IISc or TIFR or RRI, that comes to my mind. So you can shine laser in various ways and sort of trap atoms in a regular, so I'm sort of using the same color. So you shine laser and trap atoms in a regular pattern like this. Okay, so that would be like say an induced lattice. Okay, in some sense. Okay, so but those kind of things happen, but there we won't say that translation symmetry is spontaneously broken, because it is not being spontaneously broken. You're doing something to the system to make it break this symmetry. Okay, Yeah. So in other words, the underlying forces are not translation symmetric.
Thank you. Thank you. So next question is by Romita, and she asked, solid have periodicity. How is it different from symmetry of solids?
So I didn't understand. So let me draw a solid, say square lattice like this, or maybe I'll draw the honeycomb lattice of the. Okay. So this is like a single layer of graphite. Okay. So you see that this pattern has a discrete translation symmetry in the sense that unlike the laws, the Coulomb's law, for example, where the translation symmetry is continuous, this only has discrete translation symmetry because if I take this pattern and move it slightly like this, okay, you can distinguish between the two pictures. But now, if I move this red thing all the way to here, such that, of course, I am assuming that the system is infinite or very large, then I cannot distinguish between the black pattern and the red pattern. Okay, so only if I displace by discrete amounts, which is then the solid is symmetric. But this is not a property of the underlying laws. The underlying laws are symmetric under any amount of translation of two atoms. Okay, so if I were precise, and this is what is taught in grad school, is that the continuous translation symmetry breaking, continuous translation symmetry is broken down to a discrete translation symmetry breaking. Okay, so that's the more precise form of the translation symmetry breaking that I was talking about. Okay.
Thank you. So next question is by Saptarshi. He asked, by saying crystal symmetry, by saying that crystal breaks translational symmetry, are we talking about its anisotropic nature?
That is a fallout. That is a definite fallout. I have not also discussed about the rotational symmetry. It turns out that the rotational symmetry, and that's a very important question and an interesting question, that the rotational, once I break the translation symmetry in this way, the rotational symmetry is also broken. Okay, that would take a bit of time and some mathematics to explain that in crystals, the rotational symmetry is also broken along with the translation symmetry. So, for example, this only has, I have only talked about the translation symmetry, but this structure is symmetric under only 60-degree rotation, okay, not arbitrary amount of rotation, which is also a feature of Newton's law. Okay.
Thank you. I'll move on to the next question. Arush is asking, are electrons in one orbital entangled, or can they be entangled?
So the so for entanglement, you need two electrons. Okay. So that's the simple way. You can think about, if you want to think about orbitals and an electron, you can think about superposition. So entanglement is really a direct fallout of superposition between more than one quantum degree of freedom, here electrons. As long as we have only one degree of freedom, like an electron which has orbital and spin, etc., we can think about superposition of these different degrees of freedom, but we won't call it an entanglement.
Thank you. Next question is,
it is really the it's really at the heart of quantum mechanics is really superposition principle. Okay, so the superposition principle, certain fallouts of the superposition principle for many degrees of freedom is called entanglement. Okay. Sorry, Anupam.
Yeah, no, thanks. So that question comes, many have similar questions actually. Thank you. So next question is, can many greater than two, he implies what means by many, greater than two bosons be entangled?
Okay, so I don't know. Can you repeat the question? I didn't.
Yeah, so he asked, can many bosons be entangled?
Yeah,
say greater than two.
Yeah, I did not discuss bosons in this talk at all. I mean, because there was an hour. I can tell you fascinating entanglement stories about bosons where the bosons gets entangled. Okay, so you can think about bosons, two bosons, which can get entangled into sort of a pattern that is, but that would lead us to a different class of states. Okay? Yeah.
So there are 2-3 people asking similar questions. One part is, why is symmetry spontaneously broken at lower temperatures? And there is another similar question. These emergent phenomena generally seem to occur at low temperatures. Is this why physicists generally search for quantum states of matter and quasi-particles at low temperatures?
Yeah. Good. So this goes back to the slide that I deleted, but let me try to write down. So the answer to this question is third law of thermodynamics. Okay. So at high temperature, sorry, I don't know what is happening to this. Okay. So third law. Okay. So at high temperature, so let's draw the temperature axis. So this is high, okay, and this is T equal to 0, okay, or T low. Okay, let's T low. Good. So at high temperature, you know that things, each spin is doing whatever it likes. So there is a lot of entropy. Okay, but the third law says that the entropy per degree of freedom must go to 0, sorry, in the limit of temperature going to 0. I mean, I should really make this more precise, but you can look up. Okay, so then when I cool down the system from high temperature where there is lot of entropy, so S over N is not equal to 0, it's actually maximum. Okay, and then I try to cool it down. Okay, then it has to get rid of the entropy. Okay, it has to get rid of entropy to be in accordance with the third law, which we can go into the discussion, but let's not do that. Okay, so then what are the ways it can get rid of the entropy? Okay, the two organizing principles that I discussed are two ways of getting rid of the entropy. One is that you saw that the spins can sort of align in any direction at high temperature. So there is a lot of entropy, but at low temperature, they all align in one direction. Okay. So the entropy goes to 0. So the first organizing principle of breaking symmetry is just one way of getting rid of the entropy. Okay. The other way, this entanglement, generating entanglement, turns out to be a more subtle way of getting rid of the entropy. So this state, which is like any superposition of the spins, is allowed. But when I wrote down this superposition, sorry, let me just, yeah. So when I wrote down this superposition, this is one particular superposition that I have chosen. So this superposition is another way of getting rid of this entanglement, getting rid of this entropy to be in accordance with the third law. Okay, so this is why such such patterns of entanglement or such structures arise at typically at low temperature or low energies, when the system has a sort of lesser degree of freedom to move, which is in accordance with the third law. One can try to understand this in more detail, but that's one way of putting this. Yeah.
Okay. Thank you. Should I move to the next question?
Yeah, please.
Okay. Thank you. So Alok is asking, force is a classical concept. How can it be used for a quantum system?
Yeah, so I could have just used potentials, etc., and did this more formally. And this is what you would learn when you join grad school. So I just used the word force because I'm talking to a diverse audience, and B, I just have 1 hour, and I don't want to derive a lot of mathematics in this 1 hour. But you can make this statement much more precise by writing down potentials and then canonically quantizing them to get your quantum description. That would be the more systematic way of doing this. So at this point, you have to just take my word that whatever I say in words and pictures, just go over to when you try to do it seriously using, say, a book like Sakurai or your favorite quantum mechanics book.
Thank you. So his next question was how does the lattice come into being at the first place? A particular lattice needs to be a result of interaction between ions and electrons, and then you basically put electrons in the site. So yeah, that's the question.
Yeah. So it turns out that this all happens in a very cooperative way. Okay, the ions by themselves are positively charged. So if I only had ions or the nuclei, they would not form a lattice generally. Okay, I would need the electrons to make sort of provide the glue to make a certain form of attraction, certain form of interactions which are conducive to forming a lattice. But you see that the point is that an atom has many electrons. Okay, so I'm just drawing, say, I don't know, the Planck model of atom or something, but these are cartoons. Okay, so these are electron clouds surrounding the atom. So they are of different kinds. So the point is that there are many electrons. Okay, now when I think about the way that I divided up is that I divided up the electrons into the core electrons, which are in lower atomic orbitals, and the outermost electron. Okay, so the role in major ionic crystals, the role of these electrons, these core electrons, is most prominent in the formation of lattice, and they hold the lattice together. And once the lattice is there in place, what happens is that these electrons in the outer orbit, they can just hop from one lattice to lattice point to another. And that's the distinction that I made without telling it to you. These are all fantastic questions. These are things that one seriously needs to learn as a combination of physics and what in high school would be considered as chemistry. But this is really the entire nature working together.
Yeah, thank you. Thank you. So we are almost towards the end of the talk, the event. Would you take a few more questions?
Sure.
Okay. Let's then attend to them. So Sheetal has a similar question about the lattice. She's asking, electron moves throughout the lattice, then how in X-ray diffraction we get a fixed position and electrons are confined in the atom? So how they can take any position inside the lattice?
Right. I think that you know the answer to this question much better than me, Anupam. So we are basically in electron diffraction, we are basically probing this object. We are not probing these outer electrons in usual electron diffraction case. Okay. So this is what gives us the intensity. So I send in the X-ray, it scatters from this, and basically all the nuclei, including the core electrons, and that is that Bragg peak that we see as a bright spot on our X-ray plate in experiments. Okay, this is not because of these outer shell electrons, which provide us with a metallic behavior.
Thank you. Bhanu Chauhan is asking, I think he's referring to the slide that you made where you were explaining electrons are repelling each other and they would be far apart, that would be stable. So he's referring to at the time when the system of electrons will get in stable state within the metal, will they stop to move then?
Sorry, say that again.
So at that time, when the system of electrons will get in stable state within the metal, will they stop to move then?
Yeah, you know that unless we connect a piece of unless we connect a piece of metal to a battery, there is no persisting current. Okay, so the electrons would not really stop moving. Okay, but since there are many electrons, some of them would move in this direction, some of them would in that direction. So on a net, there is no motion of the electrons as far as if I don't have the battery is concerned. Of course, I have to make this description more quantum mechanical, but that's roughly how this would work out for metals.
Yeah. Thank you. Next question is again by Saptarshi. He's asking, by this description, ferromagnet should all be Mott insulators, but we know that most of them are conductors. How can this be explained?
Yeah, sure. So, actually, what happens is that the kind of physics that I discussed, there is a different way of getting magnetism, in which some of the electrons keep moving around, and some of the electrons don't move. Okay, so and those which don't move form the magnet, and that's how we get what are called metallic magnets, which turn out to be mostly ferromagnet. Okay, so that actually works out for most of the ferromagnets, but it is not true that ferromagnets necessarily need to be metallic. We know examples where we have ferromagnetic behavior, but at the same time, they are insulating. Okay, so all these questions, I think, are very important, but this would take us towards trying to understand what are the different mechanisms that are at play. So here, what I have said is that I have taken two extreme limits. Once the electrons sort of move independently or without worrying about Coulomb's law, and then the other limit where the Coulomb's law is dominating and they are stuck to their places. So these are, of course, two extreme limits. The real thing is that all electrons feel some amount of Coulomb's law, and also they have kinetic energy, they move around. In certain materials, the Coulomb's law wins out. In certain materials, the kinetic energy wins out. Now, again, because of quantum mechanics, if the kinetic energy wins out, the electrons are best thought as waves. If the Coulomb interaction wins out, the electrons are best thought of as particles. Okay, so this is again wave-particle duality playing. So we need to try and understand all these effects separately. And the effect that you described is sort of metallic magnets is somewhere in the middle, where it needs to satisfy both the kinetic energy as well as the Coulomb's law, the repulsion. So the way it does is that some of the electrons move around and form the metal, and while the others just stay fixed and form the magnet. Okay, so that's essentially how metallic ferromagnets come about. Okay, but that would take a bit more quantum mechanics to understand.
Thank you. Thank you, Professor Subhro. So actually, I'll club many similar questions together. So many people are asking, could could more than two electrons be entangled? One. Second, can entangled pairs be entangled? And third, are there any experimental signatures that we see that the system is showing some behavior resulting from entanglement?
Right. So let's try to understand this first question, that can one electron be at the same point of time form EPR pairs with two different other electrons? Okay, so that's let's ask that question. The answer seems to be no. There is something called some mathematics, some constraints on entanglement, which tells us that that's not possible. Okay. As far as whether EPR pairs can be further entangled, that's exactly what this state is, right? So that's exactly what this state is. Okay. So I have different EPR pairs. Okay, different patterns of EPR pairs which are entangled. Okay, so I have, let's focus on these two EPR pairs. So here and here, that EPR pair. So so let's focus on this electron. Okay, and this electron. Okay, so here that electron is forming pairs with different partners. Okay, and then if you keep track of this, you would find that the same two electrons form EPR pairs with different partners, and I'm taking superposition of all those. So in that sense, I am just entangling all kinds of EPR pairs. Okay, so that's one, superposing all kinds of EPR pairs, and that's one way of trying to understand things. Okay, there was a third part of the question which I have forgotten.
Yeah, actually, third part was, are there any experimental signatures of system being, components of the system being entangled? How do we know?
Yeah, so that comes from this very famous example of quantum Hall effect, or the most striking signature of the entanglement comes from this quantum Hall effect, or to be precise, fractional quantum Hall effect. Entanglement is very hard to detect, okay? And that's one of the outstanding questions. But here, because of certain other features of the system, it becomes easy to detect. Okay, so I cannot. I don't know if you see some of these numbers here, but let me point out this number. Say, let's see. This is half. Yeah, this 2/3. Okay, so this number, I don't know if you can see, it's 2/3. Okay. So if you arrange your system, and these are systems, these are basically electron gas, 2D electron gas stuck up in various kinds of other things, semiconductors and things like that. So if you take this system and do what is called measure the Hall voltage, okay? Or try to measure the lowest charge excitations or something like that. This system is made out of only electrons, okay, as far as the electrical response is concerned, okay. So naively, would expect that the quantum number of charge, okay, if you are counting charges, should be 1, 2, 3, 4 in terms of the electronic charge, okay. So integer in terms of, so you should count, but what you instead observe from these experiments is that you observe 2/3 and units of 2/3. Okay, so it is as if like the electron is fractionalized. Okay, so so this fractionalization, remember this is electron, so it's not really that the electron is torn apart, the same electron is torn apart, but it is because of this underlying entanglement pattern that it appears that the charge response is fractionalized. Okay, so this fractionalization is only possible because of this underlying entanglement pattern present in quantum Hall effect. Okay, in fact, one of the reasons why this compound ruthenium trichloride is such a talk of the town is because the kind of entanglement pattern it seems to stabilize gives rise to a particular kind of fractionalization where you seem to find that the low energy excitations, remember this is a spin system, this is magnet and all these things, okay? So the spins stuff. But the low energy properties of the system can only be explained only if you think that the low energy response is that of a Majorana fermion. Okay, now this is like some material looks ugly, black, maybe shiny, etc. But to understand, made out of spins, electrons. But to understand that the low energy response comes from in the system, you have to invoke Majorana fermion type of excitations. That is only possible because of this underlying entanglement pattern. So these are the and these are basically so the point is that these reddish blobs or this reddish area is the experimental results can be only explained in terms of Majorana fermions as far as we know. Okay, this is not yet settled. We need to try and understand this very carefully. And okay, so on the other hand, quantum Hall effect is very well settled. So this the fallouts of entanglement pattern are extremely striking, and these can be detected in experiments. Okay. Yeah, sorry, this was a long answer.
No, thank you. So, so we can, as you, I think we have addressed most of the questions, and it's already 6:15 now. So,
yeah, no, but yes, sorry, Anupam, please.
If you want to take a few more questions, because there are several questions, we can.
Sure. Yeah.
Okay, then I'll take then 2 more questions. I think that would be.
Yeah, before you start with the question, let me just say that if you have your question and that I have not answered or I have not answered perfectly, then just drop me an email. You can find my email. So my email ID is Subhro SUBHRO @ICTS.res.in. Okay, I just put some subject line like VIGYAN ADDA or something so that I can recognize your email immediately. Okay, so but sorry, Anupam, please go ahead with the questions.
Yes, sure. No, that is wonderful. Also, you can write. Also, viewers can write to outreach@icts.res.in. I'll post it in the chat, and we'll try to get the answer. Yeah. So I'll take the last 2 questions. So one question is by Pushpam. He's asking: does the fact that diamond and graphite are properties of how things come together, assemble, and not an individual atom, imply that if a collection of carbon atoms are kept in a closed box, they will arrange themselves in the form of graphite and diamond?
No, so that was that cartoon way up. So you need certain preparation conditions. You can either have that in, say, deep inside the earth, the under pressure, etc., to make diamonds or graphites, or you can mimic them in labs. So it requires some preparation condition, and that's not very different from the water and ice. So to make water to go into ice, you need to put it in the refrigerator. Okay, so you need to put it under certain condition to make it. Now, I must tell you that ice that we see is there are many kinds of crystalline forms of ice. So in cold countries, there are these snowflakes which have a different crystalline pattern to the kind of ice that we produce in refrigerators, the block ice. So these are also prepared in certain different conditions. Okay, but the point that I want to drive is that it is the same set of water molecules. Okay, so you can put the same set of water molecules under one condition, and it will give you ice of one kind, and you take the same set of water molecules and put it in some other condition, it would give you this other kind. It's so that is definitely true, but it's not a property of the water molecules themselves.
Yes, thank you. And last question is, Shreyas is asking, do amorphous solids have spontaneous breaking of symmetry? If not, long range, a short range one?
Yeah, so the amorphous solids do have some kind of translation symmetry breaking, in the sense that the atoms are stuck in random places, and the most again, these are things that we need to try and understand more very carefully, and not necessarily we know all the questions. Certainly, I don't know all the questions. You know that one of the major things that I think there's a lot of people in Bangalore who does is that try to understand the properties of glasses. Okay, the structural glass that we make our windows and things with. So the molecules are really randomly organized, or almost randomly organized, but they're stuck to that position. Okay, so in that sense, if I average over time, I would see these positions not being really uniform. Okay, the density not being uniform. Okay, but they do not provide a periodic array like a crystalline solid, and therefore we need to understand what is the reason why they getting stuck into this random set of configuration, and that I think is needs to be understood in context of amorphous solids or glasses. Okay, but if I in my definition, if I think about a random set of points, not necessarily periodic, and then try to understand whether they break translation symmetry, the answer is yes. That means then the more defined question that we have to ask is that I had a continuous symmetry, a translation symmetry group. What is it broken down to? Okay, in case of solids, it's broken down to some regular discrete translation symmetry group. In case of amorphous solids, in case of crystalline solids, it's broken down to a discrete translation symmetry group. In case of amorphous solids, what is it broken down to? Okay, that's a more concrete characterization.
Thank you. So I think we have addressed almost all the questions, or at least the questions which could be clubbed together. So we could now, I think, end the session. You have any comments, Professor Subhro? You can.
I think that it is wonderful, and if I could have conveyed some of the excitement that we have in this field, and some of you would like to be a part of this, I think then the talk has been a hit. And if you have any feedback about the talk, if you want to interact with our group, then you're absolutely welcome to do so. Okay, good.
Thank you. So let me check if Professor Gopakumar or Professor Pranav is still there. Well, I don't think so. So it has been a quite extended Q&A, but anyways, thank you, Professor Subhro, for this wonderful
I see
talk.
I see Pranav. Any question?
Oh, Professor Pranav is there?
Yeah.
You answered so many questions. I just wanted to thank you for a wonderful talk. It was very nice. I enjoyed every bit of it.
Anyway, most likely I won't be able to answer any of your hard questions, but we can talk about that later.
Okay, great. Thank you everyone for joining. This was almost 300 people were there online today. That's great. And tune in on coming this Sunday for the Copy with Curiosity talk. Can we learn from insect societies? So see you on Sunday at 4 p.m. Thank you, everyone. Thank you.